See, first we are going to start with the case when the given system is made out of point particles. Okay, but before that, few things like whenever you find mass distribution is uniform. Okay, no, when the mass distribution is uniform, in those cases, at least we can say the center of the mass is going to be same as the geometric center. And the center of the mass is going to lie on symmetric axis. And how to check axis of symmetry? Suppose if I give you a curve maybe that you know already. Suppose if I give you the curve of the parabola y equals to x square. So suppose if I use in place of x, if I use suppose -2 or if I use +2, you see the y is going to remain same or not. So whenever you replace x with -x and y with x with -x, and if y remains the same, we call it as symmetric about y axis. And similarly, if I give you a curve which is symmetric about x-axis, then upon replacing y with -y, if x is going to remain the same, for example, if I'll give you the curve of x equals y square. So whether I use y equals -y or I use y equals +y, you see x is going to remain same. Then we call it as symmetric about x-axis. And some curve that is going to be symmetric with respect to the origin. For example, if I give you y equals to x. So if you have some curve like y equals to x, so if I replace x with -x and y with -y, and if you find the equation is going to remain same, then that kind of curve we are going to call it as symmetric about origin. So whenever you have uniform mass distribution, the center of the mass is going to lie on symmetric axis. Okay. So starting with the simple case, when we have a system which is made out of discrete point masses. When the system is having discrete point masses. Suppose if I happen to know the position of the masses which are point masses in a given system, suppose M1 at having position vector R1, M2 having position vector R2, M3 having position vector R3, and even we happen to know their coordinates even, M1 having X1, Y1, Z1, M2 having X2, Y2, Z2, and M3 having X3, Y3, Z3. So to figure out the position of the center of the mass, what we do is summation of, or we'll write down M1 R1, that we have seen already, I think so, no? M2 R2 and so on.
Yes, sir.
Divided by just for continuity, I'm starting from beginning. M1 plus M2 and so on. So basically we could write it down in summation format as summation of Mi Ri by summation Mi. Same goes for XCM. It's going to be summation of Mi Xi by summation of Mi. YCM is going to be equal to summation of Mi Yi by summation of Mi, and same goes for ZCM as well. Summation of Mi Zi by summation of Mi. So this is a simple case only, and that we have seen already. Okay, next I'll take the case of if I have a system having two objects only, which is like a kind of common case, or maybe I could call it as two body system. Suppose if I have 2 point masses m1 and m2, whose position vector we happen to know, then the center of the mass of these 2 point objects will be lying somewhere on the line joining them, and it's going to divide the line joining the masses in the inverse ratio of their mass. I'll write it down. In this case, center of the mass lies on the line joining the masses and divides it inverse ratio of their mass. So wherever the center of the mass is going to be, suppose somewhere whose position vector is RCUM, and if position vector of M1 is R1, position vector of M2 is R2, then the line joining them will be divided in the inverse ratio of their masses. So that's why the RCUM is going to be same like the section formula that you will be knowing from M1 R1 plus M2 R2 by M1 plus M2. And you should know this result. Suppose if I give you a case when you happen to know what is the separation between 2 point masses are, is suppose it is D. So wherever the center of the mass is going to be, we'll divide the line joining the masses in the inverse ratio of their mass. Suppose M1 lies at a distance D1 from center of the mass, and suppose M2 is at a distance D2 from the center of the mass. So what we could do, one equation we can write down, D1 plus D2 is going to be equal to D, and D1 by D2 is going to be equal to M2 by M1. The center of the mass is going to be more closer to the heavier mass, no? And suppose this is equation number 1, this is equation number 2. You solve 1 and 2 and you will get D1 will come M2D by M1 plus M2. And D2 will come equal to M1D by M1 plus M2. And you should know it as a standard result because it may come handy in if you know the result directly, could write it down directly. Okay, I can take a new page. This thing I think I have discussed even. Just for continuity, I'm just talking about it all of it once again. Thinking that at least you know what really center of the mass is. And correct, no? We are just trying to figure out how to find that particular point, the mathematical point, which we call it as center of the mass. Okay, I can take a new page. Next kind of system that you will be coming across will be a system made out of like chunks of masses. Like for example, I have maybe one nice circle here of mass m1 whose center of the mass I know. Whose position of the center of the mass we happen to know. Suppose it is R1, then there's another chunk of mass, maybe some arbitrary mass M2, and we happen to know where is the center of the mass of M2 even. Suppose it is at R2, just a moment. Next, maybe I have one more mass, which is M3, and its position of the center of the mass also we know. So what is the result we have? Same like earlier one only. Just in place of R1 and R2, R3 and so on, we are going to use the position of the center of the mass of each chunk of mass. Okay. So here I'll write down RCUM is going to be equal to summation of MI, RI, same formula, nothing different, by total mass, which is summation of MI. XUM same goes like that, summation MI, XI, by summation mi. Same goes for ycm, same goes for zcm. So just the reference here I have the ri, xi, yi. Just a minute, someone is asking for the link. What we have is ri, xi, yi, zi are the position of the center of the mass of each. These are the position of the center of the mass of each mass chunk. So when next case is going to be when we are not going to have a discrete masses in a system like point mass or some individual chunks of masses. Instead, suppose if I have some continuous mass distribution. I'll tell you that before we go to such cases, what I'll do, I'll take a very simple case of how to determine the center of the mass of a uniform rod. So that you'll get the idea. Then only I'll talk about how to do in general in case of continuous mass distribution. Suppose if I give you that we have got a rod which is a very thin rod kept along x-axis and it is of uniform mass density. Just a moment. So what we have here is we have got a uniform rod whose mass is m and length is l, and it is lying entirely along x-axis, and we have to get the position of the center of the mass. So what really we'll do, we'll think of as if our rod is made out of infinite number of point masses which are kept next to each other so as to form a line, and each of the point mass so much small. How much small? Minimum small we can go is like atom thickness is small, no? And earlier you see when we had discrete masses which are point masses in a system, what really we were doing, we found the position of m1, we multiplied with m1, and then same thing with m2 r2 plus m3 r3 and so on. So we are multiplying the individual masses with their position vector, and then we are going to divide with the total mass, no? Correct, no? Similar sort of thing just we are going to do here. Just instead of adding up manually, we'll be doing the addition using integration. So what I'll do, I'll think of it is made out of infinite number of point masses, and if I select one such point mass which is of very small thickness dx, and somehow if I could determine what mass it is going to have, let's suppose it is going to have tiny mass dm, so we can easily find what mass it is going to be. No? So since mass is uniformly distributed over a length, so we could write down, okay, for length L the mass is m. So for unit length the mass is going to be m by L. So the mass of the thickness dx will be m by L into dx. No? So like that we have got infinite number of point masses. So this thing we have talked about earlier even, something that we call it as differential element. No? So what really the differential element is? It is the mathematical building block of a system. Not like real building block, the mathematical building block. Like for example, this rod we could think of as if it is made out of infinite number of point masses, each of them of very small length dx, but every one of them of equal length dx, correct? So in this case, what is the differential element we have? The differential element that we have is, it is made out of infinite number of point masses each one of infinitesimally small thickness which is dx. So everyone is of equal but very very small thickness dx, and from where to where this mass is going to be, I could write down as ranging from x equals to 0 to x equals to L. No? So when we were having system made out of point masses, what we were doing, we were taking one of the point mass, we were multiplying it with the position vector. Same thing we were doing with every point mass. Then we were supposed to take the sum of them, and then we divide that sum with the total mass. No, same kind of thing we'll do here. Just instead of adding up each of the point r into m or m into r, we'll be doing that addition using integration. No? So what we'll do to find RCOM, it's going to be summation of each of the point masses mi ri by total mi. So instead of doing that summation, we'll be doing the integration. And where mi is the mass of the ith point mass, instead of that, we'll be writing down dm, the mass of the differential element, into r, where r will be the position vector of the differential element, like the way ri was the position vector of the ith mass divided by total mass. Instead of summation, we'll have integration. Instead of ith particles mass, we'll be having the mass of the differential element. So what kind of system I am considering here is a system where the differential element is a point mass. No. So when differential, so I'll take the case when I have a system when the differential element is the point mass. I'll write down the case. A system whose differential element is a point mass. So first of all, what we must do to get the mass of one of the differential element, like the way we selected one small strip at some of thickness dx at a distance x from the origin. So the dm, the mass of the differential element, is going to be equal to lambda times dl, where dl is the length of the differential element that we are going to select to integrate. And what really that lambda is, it is going to be the linear mass density. In this example, that linear mass density is constant, and that is m by L. So this is something which is our linear mass density. And what dm is, it is the mass of the differential element. So in the case when we are selecting the differential element to be a point mass, so what we do to determine the RCM, that RCM is going to be equal to integral of R dm by dm. Same goes for our XCM, will be integral of x dm by dm. YCM will be integral of y dm by dm, and ZCM just like that will be ZTM by TM. And if you'll ask me what really this R, X, Y, Z are, these are the position of the selected differential element. No? So like just like the way earlier, what was xi, yi, zi, and ri were? Those were the position of the ith particle, which is one of the particle making up the system, which is having only point particles. So here r, x, y, z are the position of the differential element. I hope you understood what to do in this case. I'll solve this one. I think we've done in our class, but still just for continuity, I'm doing it from the beginning. So in this case, I have to find the position of the center of the mass. So what will be our XCOM? That will be integral of x dm by integral dm. And what dm just now we found? Dm is m by L, which is the lambda here, the uniform mass density, which is into dx. So what we get is x into m by L into dx by integral dm. And what integral dm is exactly is, it is nothing but the total mass of the system, which is the mass of the rod here. And from where to where we must integrate, anyone can tell. This rod is lying from x equals to 0 to x equals to L. So we must be integrating it from 0 to L. So you see, we have m by L, which is constant, will come outside, will be having integral x dx 0 to L divided by m. This m and this m will be gone. Integral x dx will be x square by 2, limits we have from 0 to L. And upon simplifying, it will become L square by 2L, and that is going to be L by 2. Suppose if you would like to find the YCM, that would be what? Y dm by dm. But if you'll ask what really y is here, it is the y coordinate of the differential element. You know? So what differential element I have selected? It is lying on the x-axis. So what will be the y coordinate of the differential element? It will be 0. So that is going to be 0 dm by dm, and what it's going to come? 0. And it should come 0, no? Because our entire rod is lying on the x-axis only. How thin that rod is? It is like an atom thickness thin. It is not having any thickness at all. And such kind of rod, if I have lying on the x-axis, so wherever the center of the mass will be, is it not going to be on x-axis only? So what must be the YCM? It must be 0. So where lies the center of the mass? It's going to be at x equals L by 2 and y equals 0. And that is something we knew already, because what kind of rod it is? A rod of uniform mass density. So where the center of the mass of such kind of system will be at the geometric center, which will be the middle of the rod. But I took this simple example so that you could understand that thing, which is the differential element here. Okay, I hope you got the point. So what cases we have done? System made out of point masses, system made out of some chunks of masses which are not actually point mass, but we happen to know the position of every such chunks of position of the center of the mass of every such chunk, and a system where the differential element is going to be a point mass. No? Okay. Okay, so we'll take some examples where the differential element is going to be a point mass, starting from, suppose if I have a semicircular ring. Before we get into that semicircular ring thing, if you should be knowing it, but in case if you were not there in that class, suppose if I have a point which is lying in xy plane, so we could locate that point using x comma y, the x and y coordinate, or we could locate that point by telling what distance that point is from the fixed point, which we could take it as origin, and at what angle the position vector of that point is from the reference fixed direction, which I could take it as positive x. So instead of using x comma y, I could use r and theta. No? Okay. Now Here, if I'll ask you, any point I take on this rod, what really it is made out of points only. And every point which is making up this rod is lying on the x-axis. And if I'll ask you, what is the address, what is the difference in the address of one point from another point is difference is there in x address only, no? Because everyone is having same y. The only difference I have in their address is their x position. So you see a pattern here or not? Only difference in their address was their x position. So what I did, I considered this rod is made out of infinite number of strips, each one of them of thickness x. And then I selected one such a strip at some position x whose thickness is tx. Okay. So taking that mindset, keep that point in your head. What I am going to give you is a case of a semicircular ring, a uniform semicircular ring. Tell me, what kind of mass distribution we have got here is uniform. So where the center of the mass is going to lie on symmetric axis. So if center of the mass is going to lie on the symmetric axis, anyone could tell which is the symmetric axis is going to be of this semicircular ring. Is it not going to be the y-axis? So center of the mass is going to lie on the y-axis. So we'll find that even, and you will see center of the mass says xcm or x coordinate will come 0. Because if center of the mass is going to lie on the y-axis, then x coordinate of the center of the mass must be 0. So we have uniform mass distribution. Someone was trying to join. So the center of the mass must lie on the symmetric axis. So the symmetric axis you see here is the y-axis. So center of the mass lies on y-axis. So what we can say without solving even that xcm is going to be 0, correct? And upon finding, we are going to get xcm 0 only. Now, whenever you see uniform mass distribution, then we tend to use the polar coordinate instead of using that xy coordinate. The reason is, if I'll ask you that what is the difference in the address of any point on the semicircle will be, if I use x comma y, then what you will find both x and y will be different for two different points. But if I select polar coordinate, then what we are going to have is that only difference in their address will be the angle, no? Because everyone is at same distance from the center. The only difference in their address will be their angular position. So see, earlier what we had, the only difference in their position was x position. So what we did, we thought of as if that rod is made out of infinite number of strips, each of them having different x position, but each one of them is of same thickness tx. No, same way what we do, the only difference in their address is going to be their angular position. So we will consider this ring to be made out of infinite number of strips. What kind of strips? Each one of them making an equal angle but a very small angle d theta at the center, and the angle is going to be, the angular position will be different. So just I'll write down. In this case, the differential element is infinite number of strips, each one making a very small angle, which we call it as infinitesimally small angle, each one making infinitesimally then what we do, we select one such small strip which is located at some arbitrary position, suppose theta. And what kind of element here we have? Something which is like a point mass only, no? So if I have an element which is a point mass, then how we determine the position of the center of the mass? If I want to find the x position, it will be integral x dm by dm, y position will be integral y dm by dm, where dm is going to be the mass of the differential element, no? So dm will be lambda times dl. In this case, you tell me what dl is going to be. dl is going to be r d theta, correct? And what is our lambda here? We have mass by total length, no? And what is the total length I have? It's going to be pi r. So the dm is going to be m by pi r into r d theta. So that is going to be, so dm equals m by pi into d theta. And then what I'll do, if I'll ask you what is the address of this small element is, what you will be telling me the address, theta or theta plus d theta? Theta only, no? And if I'm asking you the address where that guy is lying, is at position theta only, no? Correct. So whenever I am asking you the exact position, what you are going to give me, whatever is at the beginning of the interval, what interval I have got here, starting from theta, ending at theta plus d theta. And if I'll ask you what is the x coordinate of this guy is, so literally you will think d theta 0 and then you will report what is the x position of this guy is. So to find the x position, what I'll do, or what you will do, you will drop a perpendicular, and you can tell what will be the base of the perpendicular here is r cos theta, and the height of this guy is r sin theta, no? So this height is going to be the y coordinate, this r cos theta is going to be the x coordinate. So we want to find xcm. So xcm is going to be integral of x dm by dm. And what really is our x? And that is our r cos theta, no? And what dm is? dm is m by pi into d theta. And integral dm for this entire thing will be giving us the total mass of this ring. So this m by pi will be taken out of the integral, so it's going to become, m will get cancelled and it will be r by pi integral cos theta d theta. And obviously from where to where we are going to integrate it, from 0 to pi. Integral of cos theta is sin theta, and then when you are going to plug limits 0 and pi, for both of them sin is 0, no? So what you are going to get, this xcm is going to come 0, and that is something we knew from before. Now what ycm is going to be integral of y dm by dm, and what really is our y here, it is r sin theta. So r sine theta dm by dm is m by pi into d theta, and then dividing it with integral dm, which is nothing but total mass sum 0 to pi. If I integrate, you will be having r by pi integral of sine theta d theta from 0 to pi. If you will do, you will get it is going to become equal to 2. You check that thing on your own. So you will be having ycm will come 2r by pi, and the xcm is going to be equal to 0. So center of the mass is going to lie somewhere here on the y-axis at the distance of 2r by pi from the center of this semicircular ring. I hope all of you understood this thing, and you're supposed to remember this as a result as well. But all of you understood, no? If you want to copy, copy, and once you've done copying, let me know. In doubt? Anyone having any doubt? Okay, I can take a new page.
1 second, sir. Sir, 1 minute.
Okay, no problem. All of you understood, no, at least?
Yes, sir.
Okay. Okay, I can take a new page.
Okay, sir.
Now, suppose if I'll give you the case of a quarter ring of mass m and radius r, things are going to be quite same only. Suppose if I have a quarter ring, still what I'll do, I'll be considering element in the same exact manner, no? We'll think of it is made out of infinite number of strips, each one of them very, very small, and each one of them making a very small angle, d theta at the center. And then again, at some angular distance theta, we will select one such strip, which is making a very small angle d theta. Somehow we'll find dm, the mass of this differential element, and that will be total mass is m, length is l, and the length which is going to be, how much it is? Just a moment. Here lambda will be mass by total length. And total length is going to be, we have got a quarter ring now, no? That will be pi by 2r now. So the lambda here is 2m by pi r, correct? So the dm, the mass of the differential element will be lambda times dl. And what dl I have, that is going to be r d theta. So 2m by pi r into r d theta. So you'll see r are gone. So here dm is going to come equal to 2m by pi into d theta. And every other thing is going to be same only, no? If I'll drop a perpendicular here, what we have, the x coordinate of the selected differential element is r cos theta, and the y coordinate of the differential element is r sin theta. So if I'll ask you find xcm, so it's going to be integral of x dm by dm. And what it will be, r cos theta, and the dm that we have got here is 2m by pi into d theta by m. And now from where to where we are going to integrate it, it's going to be from 0 to pi by 2. And do the integral and simplify this thing and tell me what it becomes. How much it is coming? Same only, no?
2 r by 3.
Yeah. Do for the YCM also. Just tell me what YCM comes out to be. Same only, no YCM also. Just to integrate it, what we'll be having here is 2 by pi, 2r by pi, integral of cos theta d theta from 0 to pi by 2, and integral of cos theta from 0 to 90 will come 1. You can check that thing. So what we get here is xcm is going to come 2r by pi. Next ycm will be integral of y dm by dm. And what really our y here is r sin theta. Dm same exact thing, 2m by pi into d theta. Zero to pi by 2 divided by m. And here again 2r by pi, after simplifying it will become 0 to pi by 2 sin theta d theta is also going to come 1. You can check that thing on your own. So what we get is here XCM and YCM both are going to come same. And is it not, it is not supposed to come same. Because if I'll ask you, what is going to be the symmetric axis for this guy? Is it not the axis which is y equals to x, no? So this is the symmetric axis and the center of the mass must be lying on it since the mass distribution is uniform. So what kind of position center of the mass will have wherever the XCM and YCM both must be same? And both are coming out to be how much? 2r by pi. It means if you get to remember the first result, you can't forget this one also, no? Center of the mass wherever for the semicircular ring is, if you remember that result, you can't forget this result as well. Just the extra thing is XCM, YCM both same as the YCM of the earlier case. I hope all of you got this thing. Copy and after copying tell me. Okay, all of you are able to follow till here. Okay, I can take a new page now.
Yes, sir.
Maybe I could tell you a shortcut way to help you remember this result, because no one will be asking you find the center of the mass of semicircular ring or anything like that. It can come as a part of some bigger question where without knowing the center of the mass, you will not be able to solve anything further in that question. Okay. So there you cannot waste time in deriving it in case even if you know how to derive it. There's a theorem in math that I know from my engineering thing. I don't remember the name of the theorem exactly, but I'll tell you how that theorem works. Okay. No? Suppose if I have a semicircular ring, then one thing you can tell that this is the symmetric axis and center of the mass lies on it. The center of the mass lies on y-axis. So XCM is going to be 0. So one thing we know, center of the mass is going to be somewhere on the y-axis only. So the only thing I have to find what is the YCM is, because XCM we know, no? So what you do, you rotate this thing through the other axis through angle 2 pi. Now, if I rotate this semicircular ring, you could imagine for one full rotation, what kind of figure it's going to generate in 3D? Is it not going to generate a hollow sphere? All of you agree to it? That if I rotate a semicircular ring about this x-axis, is it not going to generate a hollow sphere in 3D that everyone could visualize? Now, you do one thing, also you visualize what kind of motion the point, the center of the mass is going to undergo. So you could tell the center of the mass is going to take a circular path whose center is going to be the origin here, and the radius of the circle it's going to take will be equal to YCOM. These two things all of you can tell now. If I rotate this semicircular ring about which axis? The x-axis. not the y-axis. And then for one full rotation, what kind of figure it will generate in 3D. And also you visualize what kind of motion the center of the mass will undergo, which will be a circular motion whose center will be the origin, and the radius of the circle will be equal to ycom. I hope all of you agree to it. So the theorem works like this. So what really we are rotating in here? We are rotating a length, correct? And what we generate upon rotating is a hollow sphere. So I'll write down formulas like that. Distance traveled by the center of the mass into length rotated is equal to the volume, not volume. What we generate is a hollow sphere and we rotate a length. So we'll say we are generating an area. So area generated. So what is the distance a center of the mass is going to cover if it is going to undergo one full circle whose radius is ycm will be 2 pi ycm. No? And what length we are rotating is a semicircle. What is the length? It has got pi r. And what we generate a hollow sphere. And what is the area of a hollow sphere is? Which is 4 pi r square. And if you don't know what is the area of the hollow sphere, then this shortcut is not for you. So what ycm is going to come 2r by pi. To explain this thing, it is taking some time, but to get this thing done in your head, hardly it will take any time. No one. Distance traveled by the center of the mass into length rotated equals to the area generated. So like that, once you know where is going to what will be the ycm, automatically you could tell what will be the center of the mass of a quarter ring will be. I hope all of you got this thing. Okay, I can take a new page.
Sir, 1 minute.
Okay, take copy. No problem. But all of you understood, no? Okay, I can take a new page.
Yes, sir.
Okay. Now see, whenever we have uniform mass distribution, we know center of the mass is going to lie on the geometric center. No, don't forget that. Next, suppose every time it may not be possible to consider system made out of point masses. So what we do, we consider system made out of something else, which is not a point mass, but it should be something whose position of the center of the mass we know. Okay, so maybe you will understand. Let me write it down first. What is the case I have now? When the differential element is not a point mass, so what it could be then? If it is not a point mass, it could be a case when the mass is distributed over some area, or it could be case when the mass is distributed over a volume. Like the way when the mass was distributed over a length, what we did, we considered it is made out of infinite number of very small lengths. So same way, if I have some mass which is distributed over an area, then we think of it is made out of infinite number of small areas where each of the area is going to be very, very small, no? So in that case, the differential element will be something which is area, or will be having a differential element which is some small volume. Okay. So those cases will be, we could call it as when we have surface mass distribution, or the mass distribution is over an area. Okay, no? So if I have a mass distribution over an area, then the differential element that we select is going to be equal to sigma into dA. Just like the way earlier we had differential element was a tiny mass which is our length. So we considered finding the mass to be equal to lambda times dl, where lambda was linear mass density. Same way here, sigma is the surface mass density. And dA is the area of the differential element. If I have mass distributed over a volume, in that case we consider finding dm, which is the mass of the differential element, using rho dv, where rho is going to be the volume mass density and dv is the volume of the differential element. Where dv is the volume of the differential element. So whenever we select the system made out of something which is not a point mass, whatever we select is it is supposed to be something for which we already know the position of the center of the mass. Okay. So what is the result in this case will be, I'll write down. So here RCM is going to be equal to integral RdM by dm. Formulas will be looking like that only, but what I'm going to use in there will be different things. Xdm by dm, we'll copy all of, we'll write this thing again, maybe I'll copy it from here. What really formulas will be looking same only. Only different thing I have here is the r, the x, the y, and the z that we use in that integral are going to be the position of the center of the mass of the selected differential element, or whatever is the differential element. The pattern is same only. Earlier when we were finding center of the mass without the use of the integration, when we had some discrete separate masses making our system, no? So when we had system made out of discrete point masses, then R1, R2 were the position of the position of the point masses only. But when we had system made out of masses which is not a point mass, then formula is same only, just we are going to use that R, X, Y and Z to be the position of the center of the mass of each chunk. Same like that in using integration, if I'm finding it out, and if I consider system made out of something which is not a point mass, then what really we do, we, we use the same formula, just we are going to use the position of the center of the mass in those formulas. No, R will be the position of the center of the mass of the differential element. X, Y, Z are the coordinates of the center of the mass of this differential element. So it means whatever I am considering the system to be made out of mathematically is supposed to be something for which we must know the result of the center of the mass. No? Like for example, if I'll think of what can be a differential element of a semicircular disk, it can be. You could take anything, but you must take something for which you know the result of the center of the mass. So I might have given that example in class also. You have seen now sometime doormats will be made out of round circular strings only, when which are tied together somehow. So same way we can think of a semicircular disk. Maybe just I'll draw it once. See, if I have a semicircular disk, so totally we could think of it is made out of infinite number of thin rings, and how each of the ring is going to be every ring of very small thickness dx, but the radius is different, ranging from, or maybe I'll take something else even. I'll consider it is made out of infinite number of thin rings, each one of them of very small thickness dr, and the radius small r is ranging from 0 to capital R, where capital R is suppose the radius of the semicircular disk. I hope you're getting the point now. So why I selected the differential element to be a semicircular ring here, because I know the result of the center of the mass. I know how to find the center of the mass of the semicircular ring. No? So what is the takeaway is whatever you could consider as a differential element totally fine, but it should be something for which you know the position of the center of the mass. So I write down here the differential element that we have got here is, so it is semicircular disk of mass m and radius r. So a differential element here we have infinite number of infinitesimally thin rings, each one of very small thickness dx. Sorry, each one of very small thickness dr, and radius varying from small r equals to 0 to small r equals to capital R. I hope you could visualize that, no, that this could be one of the differential element from which I could consider it is made out of mathematically. That is not the issue, no? That part is fine, then no problem. Then what we do, we select one such differential element and we calculate what is the mass of that differential element is going to be. And then we find where is going to be the center of the mass of that differential element, no? So what really is our differential element here? So this is the differential element, is no? So we'll select one such differential element whose inner radius, if I'll ask you what it is, the inner radius is r, and what is the outer radius? It is r plus dr. And what we have to do first is to find the mass of this differential element. No? So the dm, the mass of this differential element will be sigma into dA, where sigma is the mass density, which is the surface mass density. And what kind of mass distribution we have? Over an area distributed uniformly. So surface mass density, you could find easily what it is going to be, mass by total area. And what is the total area I have? Area of the semicircular disc, which will be pi r square by 2. No? It is going to be 2n by pi r square. Next dA, the area of the differential element. That is something how to figure it out. So maybe I could tell you via different ways. Method 1 will be whatever the dA is, it is the area. If I find the area up to outer radius r plus dr, but now we have to find the area of this thin ring. So what we could do, we could find the area of a semicircular disc up to radius r plus dr. And we can find the area of semicircular disc up to radius r. Then we can subtract them, no? So I could write down dA is going to be whatever area I have up to r plus dr minus the area up to r. Area up to r plus dr that we could find, it will be pi by 2 r plus dr square. And area up to r will be pi by 2 r square. Okay, and then what we do, we just simplify it. Pi by 2 I'll take out common. We'll have r square plus dr square plus 2r dr minus of r square. So r square gone. And whenever we have something which is infinitesimally small, then the higher power of such quantity, higher power means suppose if I have a quantity x which is very, very small, then every power which is more than 1, that is x square, x cube, these terms will be neglected. So here our dr is infinitesimally small. So dr square will be like very, very small, so we'll neglect it. So here dr square made equal to 0. Upon simplifying it, you see it's going to become pi r dr. This is one way, but I will not be solving it by this way. What is the other way is, so whatever the strip is, no, suppose if I have a semicircular strip which is made out of some rubber which I could easily flatten it on a table. Okay. So suppose if I'll flatten it on a table, that strip, you tell me how that strip will be like. Is going to be almost like a rectangle or not? And it will be like a rectangle whose width will be dr and whose length will be, see, outer inner radius almost same as r only. So what will be the length of that small rectangular looking like strip will be? It's going to be 2 pi, sorry, it's going to be pi r, no? So we have got a rectangle whose one width is dr and the other length is pi r. So what will be the area of such a rectangle will be L into B, that will be pi r dr. This is method 2, but this is also I will not suggest. What is the best way is, that is through differentiation, the understanding of the differentiation. So cover this all, I'll take a new page. Go to method 2, all of you got it, no? You have a small strip like a string only, man, which is in the shape of a semicircle, a thin string. And then you flatten it on a table. What will be the thickness? Will be dr. What will be the length? Same as the length of that semicircle, which is pi r. So what area it will be having? Pi r dr. Okay, copy fast everyone. This mic is good, no? I bought this thing during lockdown. Maitri, you know center of the mass what it is? Because you missed that class, man. I told you don't miss any class of friends. This class is more important class than this. Mm, okay. So just copy the notes. I'll tell you whatever you have missed, but still don't try to miss any more classes.
Yes, sir. Okay. Sure.
Shreya got it now. Prabhu, any doubt? Tarunika understood. You should copy and tell me.
Copy.
Okay.
Can you just show the previous slide for 1 second? I'll just.
No problem.
Thank you, sir.
No problem. Take your time to copy. See, this chapter and the next chapter, everyone must be comfortable with, everyone must understand every sentence I utter in the class and every line in your module, and you should solve every question in your module. That is like must for everyone. You want to see any kind of decent rank also, you cannot get that without becoming good in these two chapters.
Copy it, sir.
So what is the best way is that the whole reason why I did that differentiating things in so much detail, even though no one will take in that much detail, just telling you how to do differentiation, not like getting into like a real thing of that differentiation, the limit thing and all. So I hope by this time everyone is comfortable with what dy by dx means. In dy by dx, dy is the change in the y whenever I do a very tiny change in the x, which is dx. So suppose what is the thing that we need here is this area of the strip now, one that I'm shading right now. So what you do, you think of how we are going to get such area of the strip. Suppose if I have just a moment, drawing here is a little bit taking time. Board is these things are like so much faster. Teaching online is like headache, man. I don't want to take online classes just to do things in proper manner. I'm taking it. Suppose here I have a disk whose radius is r. Okay, whose radius is small r. Then I'm going to change the radius from r to r plus dr. So is it not okay to say that here area is going to be a function of r, that small r? And if I'm going to change the radius, initial radius, suppose I'm keeping it as r, and then I'm changing it to the final radius, which is r plus dr. And when the radius was r, we were having some area. Suppose when the radius was r, the area that we were having was a. When the a radius is made equal to r plus dr, the area will change. Suppose the area increases by dA. So the new area when the radius is r plus dr, we could write down as a plus dA. So whenever I'm changing the radius by dr, in doing so, whatever is the change in the area that we get, that is the area dA we want to find. No man. Suppose already I have a disk whose radius is r, then I'm going to grow the radius from r to r plus dr. And if I change the radius from r to r plus dr, then you tell me what is the change or the increment in the area I see. Is it not this shaded area? That is the area dA, the one that we are into finding. So what you do, you write down a as a function of r, which is pi r square by 2. Then dA by dr, you find it out that anyone can do the differentiation. See, differentiation or integration that you will come across in physics will not be difficult at all. What will be difficult? How to arrive at it. So pi by 2 will come outside dy by dr of r square. Anyone can do that thing, that will become pi r. No? So what we get, dA by dr to be equal to pi r. And what dA is in dA by dr? It is the dy, whatever is in dy by dx. It is the change in the area, the one that we see whenever we change the radius by very tiny amount, which is by dr. So what we get, dA, is it not the area that we want to find? No? If I grow the radius of this disk from small r to small r plus dr, in doing so, the area, the extra that I get, that is the area of that elemental or that differential strip. No, man? That elemental strip means that differential strip. Differential strip, you understand, no? The strip that we selected to integrate, or the strip from which I am considering the system is made out of, or the strip which is the mathematical building block of this disk. Okay. So DA, I hope this is it not the easiest way and most conceptual way to find DA without any confusion. We write down area as a function of R, find DA by DR, throw DR to that side. That is totally fine kind of thing to do, not mathematically wrong thing to do. You understand that? Okay. I hope you got this method 3, no? No confusion at all.
Yes.
Okay then. I'll take a new page
Yes.
to copy. Because my iPad is not like big screen. I can't write much in one page. I had a bigger screen iPad that one day in Chennai rain I got caught and I lost my iPad in that rain. Switching from big screen to small screen becomes difficult to write, man. So what I've written here is dA is the area of the differential element, which is also same as the change in the area when the radius is changed from r to r plus dr. Method 3. Okay, I can take a new page now.
Yes, sir.
Okay. Now, what is our differential element is, this is our differential element, which is a very small thickness dr and the radius of the sky is small r. So whatever the mass it has got, but it is a ring of uniform mass density. And if I have a ring of uniform mass density lying like this, where is going to be the center of the mass of the differential element? No, it's going to be somewhere here. So radius is small r. So center of the mass, I write down the center of the mass of the differential element. So the x coordinate of the center of the mass is our 0. Y coordinate of the center of the mass that we know 2r pi, no? So what we do, xcm is going to be equal to integral of x dm by dm. Same formula, just here x will be the x coordinate of the center of the mass of the differential element, no? So what is the x coordinate of the center of the mass of the differential element? That is 0. So if I'll plug 0, what will come as xcm is going to come 0. And xcm was supposed to come 0, no? Why? Because what kind of mass distribution I have? A uniform mass distribution. And what is the y-axis here is the symmetric axis. So center of the mass is going to lie on the symmetric axis. So what must be the x coordinate of the center of the mass? Should be 0 only, no? So what will be our ycm? That will be integral of y dm by dm. And what really is our y here? The y coordinate of the center of the mass of the differential element, which is 2r by pi. dm we have to plug everything we have found. dA we got it as pi r dr. And what was our surface mass density? N by total area, which is pi r square by 2. So dm is 2n by pi r square, capital R square, into pi small r dr. No? This pi we could cancel. It will become 2n by r square into small r dr. So just I'll plug the value of the dm, which is 2n by 2n by capital R square into small r dr. Integral dm is total mass only, and from where to where we must be integrating it? from small r to be equal to 0 to equal to capital R. Is it not? After that, things are like simple only. You take out common whatever, take outside whatever is constant. So what we have is 4n by pi r square integral r square dr 0 to capital R divided by m. So I can cancel this and this m. An integral of small r square will become r cube by 3, no? 4 by pi r square, and that is going to become, check it out, r cube by 3. So what is going to be the center of the mass? It's going to be 4r by 3 pi. I hope all of you got this one. Just let me draw the figure once. So you have to remember this result even. So we have got a uniform disk of mass m and radius r. So one thing is there, center of the mass y-axis is the axis of symmetry. So and center of the mass lies on the y-axis. So xem will be equal to 0. So where center of the mass is going to be lying at a distance of 4r by 3 pi from the center. And this is something you are supposed to remember even. Okay, all of you got this thing? Copy this one. After copying, tell me.
Copy it, sir.
Okay, then.
So one minute.
Just a moment. Okay, I can take a new page.
So one second.
Okay, no problem.
Yes, sir.
Okay. So for this case also, we have got a theorem for mass that you could use it. Okay, what is that? Just a moment. So one thing you can tell, center of the mass is going to lie on the y-axis, so xem will be 0. So the only thing that you have to determine is going to be the y coordinate of the center of the mass. Just like that earlier case, you rotate this thing about the x-axis through a full angle of 2 pi. And then what we are rotating now here is not a ring, no man. We are rotating a semicircular disk. So what I'll say, if I rotate this thing for one full rotation about x-axis, will generate a full solid disk, a solid cylinder, solid sphere or not. If I rotate a semicircular disk that for one full rotation about x-axis, what exactly we generate in 3D? Is it not correct to say we generate a solid sphere? Okay, so what we'll write down here, and again, what kind of thing that center of the mass will do? It's going to go around in a circle whose radius will be equal to ycum, and the center of the circle will be the center of this disk. So similar thing we have got just a little bit different distance traveled by the center of the mass into what we are rotating right now. Earlier we were rotating area, length, we are rotating an area, so I'll write down area equals to what we generate in 3D is going to be the volume. No? So here we have area, whatever is rotated, and whatever is the volume that we are going to get to generate, or the volume generated, and what it will be, solid sphere. No? So if you don't know what is the volume of solid sphere is, then this formula is not for you. The distance traveled by the center of the mass 2 pi ycum. Area we are rotating, area of half circle pi r square by 2. Volume that we generate a solid sphere of radius r, so 4 by 3 pi r cube. So this calculation you could do in your head even, no? And you can find ycm will come 4r by 3 pi. Okay, copy this thing. Okay, I can take a new page.
Wait a second, please.
Well, understood this shortcut. No? Nice shortcut, no?
Uh, in this thing, we are just multiplying the circumference into the surface area.
Not circumference, distance traveled by the center of the mass, which will be taking a circle of radius ycm. What will be the circumference 2 pi ycm? Area
Just
of the disk equals, yeah, just like that. This
I
is a
just
theorem from mass, okay? It is some use that it has got for us, so I'm telling you, okay? Now.
yes.
Okay. Now, next, suppose if I'll take a case when I have a quarter disk. So when we were having semicircular disk, the differential element that we selected was semicircular thin rings, no? So if I have a quarter disk, so what will be the differential element you will select? Obviously, it will be thin quarter rings, no? In the same exact manner, correct?
Yes.
So, okay, I can take a new page. No, let me copy it. Till then, I'll draw whatever I need to draw for the next one. Okay, I can take a new page now.
Yes, sir.
So determine the center of the mass of the quarter disk as a homework. You could, you should be able to do this thing on your own now. Just I'm telling the result even. So just like the case of the quarter ring, what will be the symmetric axis now? Will be y equals to x now. So this will be the axis of symmetry, and the center of the mass lies on it. So if any point which is going to be lying on the line y equals to x, so what will be the x coordinate and y coordinate, whatever it will have, must be equal, no? So same goes for the center of the mass as well here, xcm and ycm both will be equal to 4r by 3 pi. So the center of the mass is going to have both the x coordinate and y coordinate same. So in case if you know the result for a semicircular disk, you can't forget the result for quarter disk, but you try finding out as a homework, and you could tell what will be the differential element you will be selecting is going to be infinite number of thin quarter rings, each of them of very small thickness dr, but located at different radius r, starting from 0 to capital R. No? So the differential element will be thin quarter rings. No? Okay. Copy this thing, I'll take a new page. Okay, I can take a new page now.
Got it, sir.
Okay. Suppose if I'll give you a triangular lamina, which is a right angle triangle, whose height I'm giving you, it is h, and whose base is suppose b. So first of all, if I'll ask you where is the center of the mass, what kind of mass distribution we have? Of uniform mass density over an area. So where the center of the mass will be lying on the geometric center. And what will be the geometric center of a triangle will be the center.
Centroid. Centroid.
So suppose if just so that to tell you how that theorem works. So we don't know where is the center of the mass, but we know somewhere it is going to be in xy plane only. And suppose x coordinate is xcm, the y coordinate is ycm. And what we have, two unknowns I have. So two equations we have to frame. So what I will do, suppose if I'll rotate it for 1 foot rotation about x-axis, then you could visualize now what exactly it's going to generate in 3D.
Right circular cone.
The volume generated will be a cone whose height is going to be equal to b, and the radius of this cone is going to be equal to h. And upon rotation through 2 pi about x-axis, what will be the center of the mass is going to take? You can tell the center of the mass will be taking a circle whose radius is going to be equal to ycm, no? Correct. So what will do? Distance traveled by the center of the mass into area equals to the volume generated. The distance traveled by the center of the mass is going to be 2 pi ycm, correct? And area that we are rotating is a triangle, half into base into height. Volume we generate is a cone whose volume is 1 by 3 pi r square L. So it will be 1 by 3 pi. Radius here is b, no? B square h. And if you solve, you will see ycm is going to come equal to b by 3. Same exact thing you do. You make it to go around for full circle about y-axis. And then you will see it is going to generate a volume which is a cone whose radius is going to be equal to b, and the height of that cone is going to be equal to h. And center of the mass, you can tell, is going to take a circular path whose radius is going to be equal to xcm, no? So distance traveled by the center of the mass into area equals volume generated. Distance traveled by the center of the mass now is 2 pi xcm. Area of the triangle is half into base into height. Volume we generate is 1 by 3 pi. Radius will be b square. Height is h now. So, sorry, radius is going to be, my mistake. Here radius was h, no? So radius h square, height is b, so it's going to be equal to b h by 3, it will come h by 3. And here radius is going to be b square, so xcm is going to come b by 3. So if I have a right angle triangle whose height and base given to us, and we can tell one thing, that center of the mass must be more closer to the region, or must be more closer to the thicker part, no man? Suppose base if I give you as b, then the center of the mass is going to be b by 3 from the thicker part and 2b by 3 from the thinner part. Like that you should remember it. And height is h, then from the thicker part the center of the mass is going to be h by 3, and from the thinner side it's going to be at a distance of 2h by 3, which is nothing but centroid as well. I hope you got how to find, you should know this one as a result even. Okay, and this you must be knowing from maths also, no? Okay, take copy this thing and take a new page then. Okay, I can take a new page now. Homework for today I'll write down here. Okay. Today's homework you have is beginner box 1, question number 1, question number 2, question number 3, question number 6, question number 7, question number 8, 9 and 10. So beginner box 1, this many questions at least you will solve. Okay. Next
Okay.
you will solve exercise 1. Question number 1, question number 2, question number 3, question number 21. Okay, this many questions at least you will try before you come for tomorrow's class. Okay, and everyone is okay with the idea of the center of the mass, then no problem. Finding center of the mass is easy thing only. It is algorithmic thing. Everyone will be able to get it today or tomorrow. But main thing is to understand the significance of center of the mass, the one that we discussed in the last class. Okay. So time is also almost over. So maybe we'll end the class here. Tomorrow same timing. Don't miss the class. Okay. Tomorrow is going to be more important class because we'll be starting that conservation of momentum and things. So don't think of missing tomorrow's class. Okay. Okay. Bye everyone. See you in the next class.
Thank you, sir.